All right, so in this video, we're going to be chatting a little bit more about this kind of general idea of what does it mean for two things to be congruent. Actually, what we're going to be showing in this case is that the original definition that we have is going to be equivalent to another object. This is actually kind of touching a little bit into this world of the kind of slightly unfortunate thing about upper level mathematics is that it depends on your particular author or textbook about how something may actually be defined. So in this case, we're actually going to connect the dots between what we initially referred to as kind of this notion of congruence and what some other textbooks actually may say as being congruent. But at the end of the day, what's going to happen is that these things are actually referencing the exact same thing, so it really doesn't matter on which approach you take. You can kind of take the way that we've been doing, or you can kind of go down this new path as well. So in this case, what we're going to do is we're going to kind of build this off of this last example we were looking at. So in this case, we know that the numbers 73 and 1 are going to be congruent modulo 24. And the reason we know this is that if I take this 73 and if I divide it by 24, I know that it kicks out a 3 with a remainder of 1. So in this case, I can actually write down 73 as 24 times 3. It's this idea that I can break off 3 different 24s, and I have this extra little remainder of 1. Well, what ends up happening is that I can actually take this expression that we have right now, and I can subtract a 1 from both sides. And why I'd like to do that is I can see that I have this 73 minus 1 on the left-hand side, and then on the other side, that's exactly this kind of nice integer multiple of that 24. So that kind of connection between 73 and 24 is staring you right in the face now. You can see that if I take this object and do this reduction mod 24, that right-hand side would disappear. What's going to happen then is all I'm left with is this 73 and this 1. What this actually says, if you go back to this world of divisibility, is that this idea of taking 73 minus 1, that new number you're going to get is actually going to be divisible by 24. That is, I have that 24 divides 73 minus 1. And that's exactly the connection that this fact is going to say, is that this notion of A being congruent to B mod n is saying the exact same thing as n divides A minus B. So there's a little bit of kind of formalities that we have to get through in this case, but the kind of essence of this all is that those two definitions are actually saying the exact same. So what we're going to do in this case is think a little bit about what does this notion of A being congruent to B mod n actually say. What's going to happen is you're going to have this number A that you start with, just like that number 73. What's going to happen is that there's going to be some integer multiple of n. So in this case, there's going to be this n multiplied by some k in the exact same way that I had a 24 and a 3 over there. And then there's going to be that little remainder, that little b that exists afterwards. So that's what we have initially, is that this idea of A being congruent to B is really going to say that A is going to be equal to, it's going to be equal actually. I've dropped this kind of equivalence notation, and I'm going to just introduce this notion of equality here. So A is going to equal nk plus B. So in this case, what I want to think about then is what does this idea of n dividing A minus B actually mean? So in this case, what happens when I'm talking about divisibility is going to be that A minus B is going to equal then in this case some integer multiple of n. So in this case, it's just going to say that n multiplied by some random integer, in this case L. So here's where you can see that these connections are going to be formed almost immediately. If I add a b to both sides, that is, if I write this as A equals nl plus b, you can see this perfect connection between this thing on the left and that thing on the right. They are in a sense saying the exact same thing. In this case, you can actually be sloppy with this L because they're actually the exact same thing. This L is in fact going to be that K. There's no distinction between the two. They end up being the exact same object. So if you want to kind of see the kind of formality of what's going on, it's also kind of a nice foreshadowing on what's going to be coming. What's officially occurring in this case is if you go back to your world of all of this logic stuff, what this is actually going to be one of these biconditional statements. I'm going to have this kind of initial statement P, which is going to say that A and B are congruent mod n, and I'm going to have my other statement Q, which is going to say that n divides A minus B. What's going to happen is that I can rip this thing apart into two separate statements. So the idea is that my kind of initial hypothesis P is going to then imply Q, and then I also want to see the backwards way of happening as well. This idea that if I assume this kind of divides property, I want to go back to this world of being congruent. So what's going to happen if you're interested in kind of seeing the kind of lengthy write-up of this, it's not that lengthy, I guess, it's really the kind of just formally stating what we just got done looking at, is we're going to break this into two different directions. We have, in a sense, the forward direction, which is I get to assume that A and B are congruent, and I want to show this divides property. And I have the reverse direction where I get to now assume this divides property, and I have to go back to this world of being congruent. What's going to happen is that you're just going to see that it's the exact same step that we just saw. The idea that if I assume A and B are congruent mod n, I'm going to have that there's some random integer k, such that A is going to equal nk plus B. And then you do that subtraction by B and you're like, oh, this is exactly what the definition of divides means. For the reverse direction, you assume that n divides a minus b, and in this case, you're going to see that there's going to be some integer L such that a minus b is equal to nl, and then you're going to add b to both sides. In this case, you see that a is equal to nl plus b, and that's exactly the definition of what it means to be congruent in this case. So really, kind of there's a little bit of formality going on, but the nice thing is that if you just write down the definitions of those two things, you see that they're saying the exact same thing. What's really nice about this is that if you go back to kind of the slight comment that we've made a few times already of just kind of this connection between divisibility and congruences, what happens is that if you take this previous result and get rid of all of the b's, so in this case, if I change all of these b's to zeros, what's going to happen is that I'm going to see this fact that's going to say a is going to be congruent to 0 mod n if and only if n divides that number. And so that's going to be a really useful fact, and that's actually why I'm going to restate it as its own little theorem in this case, because it comes up over and over and over again. I actually am not a huge fan of working in the divides world. I would prefer to work in this congruence world. For some reason, in my head, it makes a little bit more sense.